what is the latest with the oceans? What is the latest in the heat content of the oceans and temperatures? Hello, friends. Jim here. Well, this is think of this as an ocean heat content update for up through 2023, and of course, the lead author, the lead researcher is Li-Jing Cheng, and a whole bunch of other folks. And I will leave the URL in the comments and description box. So let's go through the abstract. The global physical and biogeochemical environment has been substantially altered in response to increased atmospheric greenhouse gases from human activities. In 2023, the sea surface temperature, SST, right, you know that by now, and upper 2,000 meter ocean heat content, nice to see that stress, OHC, reach record highs. The 0 to 2,000 meter OHC in 2023 exceeded that of 2022 by 15 plus or minus 10 zettajoules. And as a reminder, a zettajoule is 10 to the 21 joules. So that is, if you're going by the IAP or the CAS data, 9 plus or minus 5 zettajoules if you're looking at NCEI and NOAA data. The tropical Atlantic Ocean, the Mediterranean Sea, and Southern Oceans recorded their highest OHC observed since the 1950s. Let's highlight that. All right. Highest OHC, that's ocean heat content, that's not SST. Associated with the onset of a strong El Nino, the global SST reached its record high in 2023 with an annual mean of approximately 0.23 C higher than 2022, and an astounding more than 0.3 C above 2022 values for the second half of 2023. The density stratification and spatial temperature inhomogeneity indices reached their highest values in 2023. The density stratification and spatial temperature inhomogeneity. Translation: stratification. It also might reflect a reduction in the effects of the mixed layer depth and how far down it reaches. That, of course, is going to vary depending on wind stress factors and so forth. Okay. And they give us a whole bunch of keywords: ocean heat content, salinity, stratification, climate, etc. The increase in CO2 and other greenhouse gases in the atmosphere from human activities has led to an increase in long-wave radiation trapped within the Earth system, resulting in an increase in the difference between incoming and outgoing radiation at the top of the atmosphere and causing an Earth energy imbalance. With about 90% of the excess heat accumulated in the Earth's system deposited in the world's oceans, EEI, right, Earth Energy Imbalance, causes rising ocean temperatures and increasing ocean heat content. In other words, there's more absorption by the oceans, but also contributing to the EEI. In other words, more so than just looking at radiation coming in and going out, is this heat that's accumulated diffusing back to the atmosphere. Both OHC and a closely associated sea level rise, SLR, are robust indicators of climate change because they have larger force signal-to-noise ratios than surface temperature change. This is may not seem like much, but this is an important statement. Robust indicators because they have this is the key part, larger force signal-to-noise ratios. In other words, we can more readily see the human signal, the human contribution, than surface temperature change. Surface temperature change is going to be a lot of factors that impact it and affect it that makes it more difficult to see the strong impact of human activity. So that is, an extremely important statement. And this, leads me to, I'm going to do a little digression here. But all this talk about aerosols. And the aerosols causing the SST to jump. Well, lesser aerosols may indeed allow, just less clouds, blah, 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 so more sunlight energy can penetrate the ocean. But remember, most of the sunlight energy is absorbed in the upper few meters. It attenuates rapidly. An exponential decay function, to be specific. And that is, they talk about, look at like the tropics. It goes down to 200 meters. Well, usually the tropical waters, for the most part, pretty calm. Go up into the North Atlantic, where we've been seeing some of these crazy SST increases, and it's very rare you're going to have calm conditions out in the North Atlantic. So with all that waves and turbulence and and choppiness and fetch and so forth, sunlight energy is really not going to penetrate too much in the ocean. So this whole notion that, AMOC is slowing because of aerosols and aerosols causing the jump in SST, I'm like, no. If it does, it's going to be extremely minimal, certainly not the main factor, the main parameter. There's going to be other parameters, and that's the ocean heat content. There's also another point to mention here, something that atmospheric scientists do not consider in their modeling, especially those looking at EEI and aerosols, and that is the role of phytoplankton. Many phytoplankton groups release DMS, dimethyl sulfide. Yes, they release aerosols. And recent studies have shown that when the planet warms, the phytoplanktons release more DMS. And when the planet cools, they release less. So in other words, nature has her own aerosol masking effect, and the phytoplankton have a major role in regulating Earth's temperature. Just as they produce some 50 to 80% or so of atmospheric oxygen, well, it makes sense that they're going to, the Earth's pretty much a watery surface. They're going to help control the temperature. So this is something that atmospheric scientists omit. They do not even consider. And so they are presenting a vastly incomplete picture when they talk about aerosols and EEI and so forth. So I wanted to mention that the phytoplankton play a major role in Earth's temperature regulatory processes. Nature has its own aerosol masking effect, which is a negative or corrective feedback loop. So you may reduce the aerosols from burning fossil fuels, and require burning fossil fuels with a lower sulfur content, but the phytoplankton will offset that by producing more DMS. Now, a potential problem is with the increasing stratification. If nutrients are used up or not injected into the photic zone, then yes, the phytoplankton biomass, chlorophyll content, that is how we usually measure it, will decrease, which means less DMS. So that is a major concern. But that still, this needs to be accounted for. And by the way, the amount that of DMS that's produced by the phytoplankton is not insignificant. It's on the order of tens of teragrams. That's something like 10 to the 15 or something like that. So it's substantive. There is one other factor I wish to mention, and that is a factor that impacts the sun energy that can be absorbed by the ocean. In addition to the fact that the energy attenuates rapidly following an exponential decay function, you have to look at the angle of the sun and the season. So basically, this little diagram here, we see that as you go to higher latitudes, because the Earth is a curved surface, the sun energy is spread over a wide area, as indicated by this yellow arc. Whereas if you get closer to the equator, or between the two tropics, Cancer and Capricorn, it's spread over a narrow area, as we see here. The red arrow indicates the direction of rotation. So, right, different parts of the Earth receive different amounts of solar radiation because the sun's rays strike the Earth's surface most directly at the equator. As you move away from the equator, you'll notice that different areas also receive different amounts of sunlight in different seasons. And you can see, right, concentrated, it starts spreading out, and it's really spread out, which means the more spread out it is, the less energy the surface will absorb, whether it's land or the ocean. Well, the North Atlantic is kind of in this realm here. So even if the reduction of aerosol allows more sunlight through, that energy is going to be diffused. And the assumption is that the water surface is calm. It's not. Usually, if it were calm, you would have more absorption. But because of the wave action and the turbulence and other agitations, that energy from the sun, not much of it is absorbed. So this is further evidence that what we're seeing for the record high sea surface temperature is not from aerosol reduction. It is from the ocean heat content already contained therein, and that is diffusing upwards. Any sunlight energy is going to be impacting the upper few meters, especially at higher latitudes versus the lower latitudes, right? Notice the low angle of incoming sunlight. Now we can calculate, here's a normal surface. We can calculate how much of that energy coming in is actually absorbed, and it'll be a function taking the cosine of the angle. That's, it's sort of like when you're calculating forces and you break it down into the horizontal and vertical components. You do what? You take the cosine and sine aspects of the angle made to get those components. Well, sunlight energy is coming in like so. The surface is this way, so we make an angle, right? You construct an orthogonal angle, and then you take the cosine of that, and that basically breaks it down. So let's say, for example, you have 1 watt of energy coming in, and the angle it makes with the surface is 45 degrees. Well, the cosine of 45 is 0.7. So really, it's 0.7 watts that would be absorbed, assuming a smooth surface. It's less the choppier it is. So this is another factor that needs to be considered. Another factor why I contend that reduction of aerosol does not lead to the massively high sea surface temperature we're seeing, does not lead to AMOC shutdown, slowdown. And don't forget, you've heard me say this millions of times, the specific heat of water is much, much higher than air. So if reduction of aerosol only results in a 0.42 C increase in atmospheric temperatures, it sure is not going to result in a 5 to 7 C increase in ocean temperature. Okay, back to the video. But this is important. It needs to be mentioned because I'm just not seeing this mentioned. And quite honestly, it's driving me nuts. It's like the atmospheric folks, ignored the oceanographers, and the oceanographers actually take into account atmospheric processes. Like, for example, when I was, constructing heat budgets and stuff like that, I considered the, processes in the atmosphere. So when they're looking at their EEIs and constructing their heat budgets to examine that, why are they not including, the heat content of the oceans and its contributions to the atmosphere? It's, I will admit, it can be a bit, well, not a bit, but it's frustrating. Okay, further ocean freshwater change reflected in changes in ocean salinity aggregates changes in the atmospheric water cycle and ocean circulation, and these changes, along with temperature changes, regulate ocean currents, impact the vertical stability of the ocean. Ocean salinity trends are generally characterized by a fresh gets fresher, salty gets saltier change pattern, meaning areas that are currently fresh are becoming fresher, areas that are currently salty becoming more saline. For example, fresh getting fresher. There's a with lots of precipitation, riverine input into the Arctic. That's an example of getting fresher. Look what's happened to the Arctic Ocean halocline. And salty getting saltier. Just look at, for example, the intertropical convergence zone, right down along the equator, and just a little bit north and south of it. So you have that process undergoing. And by the way, a lot of these concepts here, like see, for example, Cheng et al. 2020, were discussed in my prior 2 ocean heat content videos. So this is kind of like the update of the update, or the update to the update, whatever. But yeah, this is my 3rd major ocean heat content video. This is important. These ocean temperature and salinity changes are not spatially homogeneous. So the changes are non-uniform. So the variance of the 3-dimensional upper 2,000 meter ocean temperature field have increased, meaning there's more stratification. Vertically, the ocean temperature and density structures are altered. In other words, typically when you get below, a good ways below the pycnocline, you pretty much have uniform characteristics through the water column down to depth. That is no longer the case. So we're seeing changes in the vertical stratification, which impacts the vertical. The key word is vertical vertical exchanges of energy, water, carbon, nutrients, other substances, other gases. The year 2023 began as the third year of a prolonged La Nina that faded by April, as sea surface temperatures in the tropical central and eastern Pacific rose with the onset of a new major El Nino. And they refer to this figure right here. I'm not able to enlarge these, so my apologies. But again, you can always feel free to pause the video at this point and study. Now, this is the index, Oceanic Nino Index, ONI. It used to be called ENSO, whatever. But, so this is a calculated non-dimensional parameter. It's a value, so there's no units attached to it. And typically between negative values are La Nina, positive values are El Nino, typically between minus 0.5 to positive 0.5. If you have an ONI with values in this interval, it is considered to be the neutral state, so it's neither El Nino or La Nina. A weak El Nino, a weak La Nina is between 0.5 to 1, minus 0.5 to minus 0.1, respectively. And then you do 0.5 increments. So 1 to 1.5 is a moderate El Nino, minus 1 to minus 1.5, moderate La Nina. 1.5 to 2 is a strong El Nino. Minus 1.5 to minus 2 is a strong La Nina, and anything greater than 2 is a very strong El Nino. Anything less than minus 2 is a very strong La Nina. Now, the last time we've never had very strong La Nina since 1960. We have had, on 3 occasions, very strong El Ninos. So most of the La Ninas are basically in the moderate, they're either weak, moderate, and with just a handful of strong in the last 20, 25 years or so. The last time we had a La Nina with an index reaching minus 2 was back in about 1974 or so. The recent La Nina that ended was actually on the weak side. And here's the current El Nino. And by the way, recent indications I've seen indicate that we're actually coming out of the El Nino, going back into a neutral state. And even though this might have been a strong El Nino, in some ways it actually was underwhelming and underperformed. Rick Toman on his Alaskan Arctic climate blog was just discussing this. So you can see the what's going on with the ENSO cycles here. Now they go through a description when giving you lots of data and so on and so forth. As I said, I will leave the URL if you are so inclined to read through the nitty-gritty details. Have at it. The abstract sums it up pretty well. They again discuss, and there's a wee bit of mathematics here, a nice little triple integral and so on. So they're looking at various changes in salinity and ocean heat and so on. So this is probably the most important instrument oceanographers use, the CTD instruments: conductivity, temperature, and depth. Conductivity actually measures the electrical activity in the oceans because there are ions and conducts a weak current, but you can measure it. And from that measurement, you can there are calculations to determine the salinity. Then taken together with the temperature, you can then use those two to determine the density. And we then plot all that stuff out. I did a video called All About Salinity. I discussed this all in gory detail. So if you haven't seen it or it's been a while, take a look. So, won't bore you with the mathematics. So, global ocean changes of the heat content of salinity and stratification. The global upper 2,000 meter changes since 1958. Figure 2. Hey, we're familiar with this by now. Right? Remember? In fact, I think right there, right? In my assessment, this is when the planet went past the tipping point in the mid-90s. This is when the ocean heat really started accumulating, and it keeps accumulating. So there's been unequivocal ocean warming trend in recent decades. The upper 2,000 meters of the world's ocean has warmed on average by 6.6 plus or minus 0.3 zettajoules per year and 5.4 plus or minus 0.4 zettajoules per year during 58 to 2020. And so first one is 58 to 2023 and then 58 to 2022, depending on which groups are doing the analyses. However, these trends do not match within the error bars, probably because, one, conservative assumptions by NOAA when there are no data, especially in the present of global warming trend, and the difference in the XBT, MBT bias correction. That's a statistical analytical method. Regardless, there's been a 2 to 3-fold increase in the rate of increase in ocean heat content since the late 80s. The IAP trend within 58 to 95 of 3.1 plus or minus 0.5 zettajoule per year is higher than the previous release in Cheng et al. In 2023, mainly because of the new inclusion of the bottle data bias correction. After 2007, with better global coverage of ocean subsurface data, OHC uncertainty is reduced. There is a significant warming trend of 10.8 plus or minus 1.2 zettajoules per year. Ocean heat content tends to peak shortly before, then decline during and after an El Nino event associated with ocean heat release into the atmosphere, mainly through increased evaporation. So why does the ocean heat content reduce? Because the heat's going to the atmosphere. And guess what? It's contributing to the EEI. Because when it's released, it's going to be released in the form of long wave. So, where's that ocean heat going? Seems to be, doesn't seem to be increasing as in the past. Where's that going? To the atmosphere. Get an El Nino event? It's going to go to the atmosphere. And guess what? To get to the atmosphere, it has to go through all the ocean that's above it, which includes the surface. So that also explains the major rise in sea surface temperatures. Again, it's not aerosols. Aerosols may contribute slightly, very, very, very slightly. It's ocean heat content, folks. Let's just settle this once and for all. And remember my comments earlier about phytoplankton and DMS. So El Nino events allow for the release of ocean heat content to the atmosphere. La Nina events will allow a higher accumulation of ocean heat content, which will be released the next time an El Nino rolls around, especially a strong one. That's basically what he's saying there. Right? And that's it. These are the two different data sets here. It's pretty much the same graph. Right? The anomaly. They have this pushing basically 300 zettajoules. You can see the incomplete, they're using penta data, basically 5-year running averages. That's why the vertical bars stop at 2020, because we haven't gotten to 2025 yet. The upper graph is what Cheng uses, and they use annual. They do a 12-month running mean. And the baseline, by the way, is 1981 to 2010 in both cases. So because they're doing an update of this year by year and not waiting for the 5-year averages, this one is able to tease out certain effects and is a more refined, focused down assessment. So what's the 5 hottest years of the world's ocean since 55? Well, look at this here. What do you notice? The 5 hottest years have been the last 5 years. 2023 was hot in 22, which was hotter than 21, which is hotter than 20, which is hotter than 19. That's crazy. During an El Nino event, there is heat redistribution from the 100 to 500 meter layer into the upper 100 meter layer, yielding higher SST than normal. What did I just say a few moments ago? Bingo, it's right there, right? Let's highlight that. I really just want to send this to all the atmospheric scientists. And basically, start considering the oceans. There it is, yielding higher SST than normal. The anomalously high SST leads to a higher global mean surface temperature, abbreviated as GMST, right? Global mean surface temperature. Because, wait for it, 70% of the Earth's surface is covered by ocean. And they're showing global mean surface temperature. Okay. So this is figure 3. The baseline, again, is 81 to 2010, that 30-year period. And these are just, this smaller box is your actual temperatures. And the graph itself is the anomalies. And there's the departure from this. And what do we see? Especially starting from about the mid-70s or so, is just going up and up and up. So the black line, I'm looking at the main graph here, is the annual value. The red is the monthly value. So that's why I see a little more variation. The within-year variation of SST is what's shown here. Okay, and that is the actual temperatures. And as you can see, 1955 is down at the bottom. It's the coolest. It gets warmer and warmer and warmer. This black one here with the data points, that's 2023. And if you look at this, you can see that starting about April or May or so, it really starts to having a greater and greater departure greater value than from 2022. It's unmistakable. So it goes into the discussion of regional patterns of ocean warming and salinity. So let's take a look at that. In fact, they call it the SC index, which is basically it stands for salinity contrast. So the salinity contrast given in grams per kilograms, okay, monthly means again. And what this is showing is that, and this again for the upper 2,000 meters, is that overall the ocean seems to be getting saltier. Overall. So the upper 2,000 meters salinity contrast index reveal a robust increase in the salinity contrast index in the past 50 years, indicating an amplification of the 0-2,000 meter salinity pattern. It reached 7.2 milligrams per kilogram in 2023, but they report this in grams. It's interesting. Okay. One of those places is a typo. The fourth highest value since 2023. However, the difference between the top 5 years, 2017, 22, 21, 23, and 19, is not statistically significant because of the large interannual variability and data uncertainty. Ocean density stratification also increased since the late 50s because of the change in vertical temperature, right, and salinity structure. The spatial inhomogeneity index of ocean temperature has also increased since the 1950s. This index reached a record high of 0.093 C in 2023 relative to the 81 to 2010 baseline, indicating a substantial increase in ocean temperature spatial variance. The non-uniform upper ocean warming, which is more rapid at mid to low latitudes, was mainly responsible for this index increase. Spatial maps of the 2022 ocean heat content anomaly relative to the 81-2010 conditions, figure 5, which we'll get to in a moment. This is figure 4, so figure 5, we'll look at that in a bit, reveal that most of the ocean areas are warming significantly. While some areas, much of the Atlantic, North Pacific, Western Pacific, and Southern Ocean, are heating at a faster rate than the global average, 0.8 gigajoules per square meter per year. Gigajoules 10 to the 9. So, here we see the change in the salinity contrast index, right? Here's that 0. The high value they talked about. Here's the spatial inhomogeneity, or the temperature change. And look at this here. So now, again, I point out to you, where do we start seeing this change? Let's see if I can do a little freehand drawing. Approximately here. Approximately here. In other words, if you look at both of them, we're talking the mid-90s to 2000. Just like here. Right? Just like there. It's right there. This is when the ocean started changing. The structure of the ocean are changing. Here's figure 5. The annual ocean heat content anomaly in 2023 relative to 81-2010 baseline. So this is just 1 year, 2023, compared to this 30-year average. And look at the Atlantic, north and south. Holy crapola. It's much warmer. the North Pacific. And here's the Southern Ocean. So why is this section of the North Equatorial or North Temperate Pacific waters a little cooler? Well, what they say at the outset, 2023 for the first part of the year was a La Nina conditions. So you're going to have a lower SST. Wasn't towards the end that the El Nino started forming, and that's what we start seeing here. And this is probably some deep water formation coming off Antarctica. Now, here's the kicker. So this here, okay, this is overall for 0 to 2,000 meters. So it's looking at the entire water column. But, of course, it takes a while for the heat at the surface to make its way down to depth, and even longer as vertical flows slow down. So now, figure 6, okay? Figure 6 is the difference of annual mean upper 2,000 meters from between 23 and 22. There's the 1 year change. The zonal ocean heat content are presented on the right-hand side of the spatial map. So they're basically calculating, they're integrating over the water column the heat content. And as you can see, there's some strong signals at about the equator. But take a look at this. Equatorial Eastern Pacific showed the biggest difference. And then you have pockets, and this is surprising, but again, this is average over 2,000 meters, but you see some warmer situation, off southeastern Greenland, off northwestern North America, and then right off Portugal. I'll explain that later on in the video. And now, figure 7 looks at the salinity anomalies. Okay. The upper 2,000 meters salinity anomaly in 2023 relative to the 81-2010 baseline. And then that's the upper panel, which we'll talk about in a moment. The lower panel looks at the difference between 22 and 23. And then they give you the zonal anomalies over here. So what do we see going on here? This is given in grams per kilogram salinity. So we see in the western temperate North Atlantic basically a much saltier condition. And if you look in the Mediterranean, the same thing. Look in the South Atlantic. Look in the South Equatorial Pacific waters. Look off the Saudi Arabia. This is where it's getting saltier. We see basically along the Pacific Northwest coast following the Aleutians, and then the upper portion of the North Pacific gyre is a little saltier. But why this here in the North Atlantic? Well, this is the Gulf Stream. AMOC is slowing. It's slowing down. So when it slows down, the heat transfer between low latitude and high latitude is reduced. So less warm water is going to make it up to like Iceland and Scandinavia and the UK islands and so forth. So it's going to get a little cooler there. But with that, and then you add in the melt of the Greenland ice sheet, you're going to have a decrease in the salinity. And you're going to have an increase in the temperature down here, a decrease in the temperature here. You're going to have an increase in the salinity, a decrease in the salinity. Because the gyre here and the Gulf Stream are not going to stop. They're not going to collapse. That's another silly stuff I'm sick of hearing about. What will slow down is the North Atlantic drift, which is a branch off this North Atlantic gyre, which is a branch of the Gulf Stream. That is slowing down. That will result in reduced deep water formation, not aerosols. And that's what we're seeing here. And then the change in 1 year, to be quite honest, what we see is, basically around 80 meters or so. 80 north latitude. Not meters. 80 north latitude. So that's what we're seeing, greatest salinity changes. Look here off in Alaska. There is some indication that with the riverine inputs coming in, from the Eurasian side and like the Mackenzie River Delta, which is right here, that along with the clockwise flow of the Beaufort Gyre, it is trapping that freshwater dome. And it could keep it trapped there, or it could release it, and then we get a freshwater flush into the North Atlantic. So we have to keep an eye on that. So that's what this dark blue is reflecting. This is basically reflecting riverine water being trapped. Now, granted, it's over 2,000 meter, but a lot of it is in the upper, 50, 80 meters, depending where the halocline sets up. Something else, that's another little thing going on as well. Okay, so let's look at region by region. Okay, here we go. So I think it's a little easier to look at than looking at it sideways or twisting your head around. So anyway, so here the regional observed upper 2,000 meter ocean heat change from 58 through 23 relative to the 81 to 2010 baseline. Time series are the black lines, they're smoothed away. The gray shaded areas are the 95% confidence intervals. Gray looks more like blue to me, but whatever. So let's start in the Northwest Pacific. All right. And follow, the A, right? A is this box here, right? And so on. So what we see here is this region of ocean right there. And really does not do much. It does start increasing. It's pretty much, if you were to look at the slope of this line here, it would be insignificant. It would be basically zero. Lots of error, probably due to the nature of the measurements. And you're going to see that. If you look at the earlier years, there's going to be a greater, 95% confidence interval because of the greater error. So there's more uncertainty. You notice that with the refinement in data collection and techniques and so on, the confidence interval really gets small. That means we're increasing our precision. We see that pretty much in all of these figures here. So a little bit of an increase in the early part of this century. Indian Ocean. That, of course, is over here. That's B, right? Follow the lines there. And again, a lot of errors here. And then starting in 2000, we see the ocean really, we can see a significant increase here. Now, the units that they're using are gigajoules. That's 10 to the 9th per square meter. Okay, that's per square meter. Okay. So we're seeing a big increase here. So now, sticking with the North Pacific. Okay, so the black box is northwest. The North Pacific is this blue box here, light blue box. Looking at this, there was actually a bit of a decrease in ocean heat content in the 70s into the 80s, but then there's a reversal, and we see that it is much higher. Now, do note that the scaling is not the same for each of these panels, right? Indian Ocean goes up to basically 0.9 or so up here. Northwest Pacific 1, North Pacific 1.2. Okay, so careful at that. You know that the scaling is a bit different. Then the Southern Ocean. Look at the Southern Ocean going up. A lot of heat being absorbed down there. We'll start on this side here. We'll start with the tropical Atlantic. Very small region, includes like the Caribbean islands and so on. And what do we see? You know, the heat's just going up. And by the way, the green dashed line is this baseline. Okay? And you can see, basically since the turn of the century, everything is above the baseline. Some cases started increasing before 2000 was reached. That's the tropical Atlantic. The purple box, North Atlantic. That's just rip roaring away. Look at that. And it's been steadily increasing since the 60s, but really accelerated since the turn of the century. And then, look at the Mediterranean. And we see with the Mediterranean, you notice this has the highest scaling. It goes up to 1.5. That's pretty amazing. That's 1.5 gigajoules. Well, it's 1.5 times 10 to the ninth. Wee bit of heat. But look at that. That's just ramping up. Absolutely ramping up. But now what I want to do is I do want to go back and take a look at this one here. Now this is from my last ocean heat content video that I did. And you can see that the diagrams are very close. They're very close in their plots and stuff like that, which kind of makes sense because this is really just, you know, a difference of 1 year. So basically just added on new data. But, you know, you can go back and forth between these and look at these yourself. But the data is very, very close. Same baseline. So they haven't changed the methodology. Right? They say joules per square meter, but then they'd say times 10 to the 9th. So the only difference was they said they just put the letter G in here, and G is, of course, 10 to the 9th. So that's the only difference. It's the same units. It's the same amount, you know. But yeah, they're in essence the same, those two. And again, they go on to describe what's going on with the Mediterranean. Now, I do want to look at the Mediterranean because this is it's a small body of water, but it is a very important body of water. So let's see and I will talk about that figure in a bit. The Mediterranean Sea ocean heat content in 23 was higher than 22 by 0.31 gigajoules per square meter. This is a record high. A marked temperature increase has been measured in the last few decades in the Mediterranean Sea, starting with the eastern basin, where warmer and saltier intermediate waters formed and spread towards the western basin on their way back to the North Atlantic. Keep that statement in mind. Indicated clear warming in the 150 to 450 meter layer that started in spring 2013. This warming region extended deeper and northward, reaching 700 meters in 2016. The linear rate calculated for the period 04 to 23 is 0.025 degrees centigrade per year. And it's 0.027 degrees C per year in the Sicily Channel. So, this is the transect we're discussing this. Okay. Temperature anomalies. 1999 to 2023, the baseline 81 to 2010. So the temperature anomalies. Blue is cooler, red is hotter. Brown is like really whoppingly hot. And don't forget, water has a high specific heat content. So, what do we see here? Starting September, right? They do September, March, right? So they're looking at September, oceanic summer, March, oceanic winter. Basically looking at where it's going to be the warmest, where it's going to be the coolest. So you would expect to see cooler temperatures. Right? And these are the years. So September 99, December 00, right, 2000, September 2005, March 2012, September 2014, right? And so on. So once they get past December, then they just alternate between September and March, which makes sense. So we see what? When we initially, as they described, it was about, the 150 to 450 meter layer right in here. That's intermediate water. Might be a bit warmer, but it's saltier, so so it'll be found. So it has higher density. So even though it's warmer, because of the higher salt content, it will be more dense. So you find it a little deeper, right? And then we see from below 450 or so, it's cooler, right? Cooler temperature. Then look what happens starting around, in 2014. We see the temperature anomaly down to 450 increasing, getting warmer, and now the bottom layers are no longer cooler than the baseline. They're indeed warmer than the baseline. And here, okay, so A shows the transect, B shows the temperature anomalies, and C is basically the temperature values computed in the layers of 100 to 700 meters. Right? And then the monthly mean temperature values of 400 meters from the Sicily Channel mooring. So the red is the Sicily Channel moorings, and the black is this temperature anomalies, down to 100 to 700 meters. So there was a bit of a cooling in 2018 or so, but then it comes right back up. The Sicily overall, we see a warming, as indicated. These data points reflect what we see here. Okay, and it continues. Now, out of curiosity, this was from last year. As you can see, the temperature anomalies from 99 to 2021, and then the temperature anomalies from 99 to 2021 compared to the baseline of 1981 to 2010. This figure here is very close to this figure, right? Which was the way I can pull them up side by side. But you can see how it's so much warmer, especially at intermediate depths. Here's the average temperature. and they fit in this regression line, which shows a linear increase. Now, in my last ocean heat content update video, I then said, well, okay, they're going back to 99 and they fit this regression line. I then made the argument, what if we fit a regression line from, say, 2012 to, through, say, 2017? In other words, right here, right when I'm drawing the cursor, look at that. Look at what that slope would be. By the way, it's the same transect. But this shows a massive change, an acceleration, if you will, in the warming. And in my prior OHC update video, I actually calculated that slope. Check that out in that other video. So, why is the Mediterranean important? Stay tuned. Now I want to show you this. This is a three-dimensional field of oceanic temperature changes in 2023 relative to 2022 in the North Atlantic Ocean. This is a new graphic by Cheng. You remember when I showed you, and I'm going to pull it up again, and I showed you this one here in my last OHC video. This is for the Pacific, and I said at the time, I would love to see a similar thing done for the North Atlantic. Well, careful what you wish for, because he has done so. But while we have this here, let's review this, right? This is showing the temperature anomalies. They're breaking down in 0.5, 1.0, 1.5, 2.0 isosurfaces, right? That's a departure from the baseline. And we can see all this heat. All this heat in the ocean waiting to diffuse to the atmosphere or jack up the temperatures for the SST. And we can see some constant, right here. This is just really hot in the western North Pacific and some hot spots in eastern North Pacific. Right, here's the Aleutian chains right here. But look at that. Very strong, down to 400 meters or so. This is, and again, the units would be, because this is the overall, then the units are going to be in zettajoules that this is based on. Right? When you have these temperature anomalies, that means it has to be heat in the system. Calculate the specific heat for water. It's a lot of heat that's gone into the system. And here, and this also kind of gives us a clue into vertical movements and structuring of the water layers. But there's the distribution of heat energy for the North Pacific. So I want to include that as a kind of a bit of a review. Now, the North Atlantic. So this is just the temperature anomaly, just the difference between the years. Right? 2022 is a very warm year. 23 was a hotter year, and it was warmer than 22, another record-setting year. And we're seeing, so this is the difference just in the temperature anomaly, which reflects that difference in the heat content that we discussed earlier, that they're measuring in gigajoules. Right? So for a little orientation, South America, here's North America, right? Africa, Portugal, Gibraltar Straits. What do we see here? Okay, now they're taking this from 0 meters to 500 meters, and this one's a little harder to delineate than the other one, but that looks like it's about 100 to 200 meters here, and these are down to about like 100 meters or so. This is telling me, first of all, we see what? we see that it's really, really warm. It gets really warm on the eastern Atlantic. It starts increasing in the warmth, starting basically at the Sargasso Sea and heading eastward. And it's really hot here and here. Oh, what is that? That is Mediterranean water. Remember I just showed you this heat down to 700 meters or so? Hello, here it is. Here's that very warm Mediterranean water. There's the signal right there. It's warm because of its high salt content. It's intermediate. When it exits Gibraltar, it becomes the North Atlantic intermediate water. And we all know what it does at this point. It makes a beeline to Fram. Bringing all that heat into the Arctic Ocean. Though that's why the Mediterranean is important. Right? That's why this heat is important in the Mediterranean, because it ends up in the Arctic Ocean and helps Atlantify it. It helps create havoc with the sea ice. One other thing I wish to point out to you. See kind of this little shadowy line here between the layers, right? That's down to about 100 layers or so, 100 meters or so, and we got another one down here, a little deeper, whatever, and a core warm water there. This is showing the stratification. Right? These are showing the stratification, the increasing stratification. Hence, when he talked about the inhomogeneity, you can see it right here. If this was homogeneous, we would have like basically the same color. But we don't. Got a little cooling spot, warming spot, in between spot. This very dark blue here, right? That's basically Labrador water, Labrador current, Greenland melt. Right? But we are starting to see the impact of the slowing of AMOC as indicated here. The Gulf Stream is not going to stop. As long as the Earth keeps rotating, it's going to keep, has to keep balancing geostrophic forces and vorticity and Coriolis. Has to balance all of those things. So there always will be a gyro. The North Atlantic Drift is another story. So we can see here very clearly indications of stratification and the very clear Mediterranean water, which is now North Atlantic intermediate water. We see very clearly that signal which ends up in the Arctic Ocean. So that kind of wraps up the latest ocean heat content update video. Oceans are warming and getting warmer and warmer and warmer. And right now, that loan is going to be called in, that heat energy loan. And it's happening. We are measuring an increase in diffusion of heat energy from the oceans to the atmosphere. It is more so during El Nino events. La Nina events, it tends to build up the reserves, if you will. Then El Nino releases the reserves. And by the way, there's new research indicating the importance of mesoscale eddies in basically communicating between atmosphere and ocean. These because there's vorticity involved with mesoscale eddies. It's going to be mixing, and it's going to interact with the oceans, and it's going to mix in CO2, heat energy, other gases, and so forth, and distribute it. In the past, along with thermohaline flow, mesoscale eddies help get the heat energy and the CO2 into the ocean. Thermohaline flow sequestered it to depth. Again, when folks say aerosols is causing the ocean to warm up, it's like I really just want to smack them upside the head. I just do. I know, not very scientific protocols, but I'm trying very hard to get them to understand the role of oceans. So that's another interesting thing, and I think I have I'll be doing a deep dive video on one such study looking at mesoscale eddies. So I think I have that saved up somewhere, and I got to study the paper, and then I'll make a video. But in the past, mesoscale eddies, thermohaline flow, for vertical of course, helps take heat, CO2 sequestered to depth. That's all changing. We're seeing the ocean stratified. We're seeing the heat content accumulating more so in the upper 500, 700 meters, but down to 2,000 meters, but more so, as I just said, in the upper several hundred meters. And that heat is being returned to the atmosphere. And that's a lot of energy, over 93%. You look at the thumbnail I did on the ocean heat accelerating, or sea surface temperature accelerating video. Where does the heat energy from burning fossil fuels go? 93% to the ocean, 2% to the atmosphere. And that's causing all the craziness that we see. But we have the ocean heat being returned to the atmosphere, right? This is a major reason why cyclonic storms are stronger and have more energy, because of sucking up the energy from the ocean. And of course, the oceans are warmer. Warm energies really fuel cyclonic storms. Hence, you get a big wallop of a storm. So there's your update. What the latest is for ocean heat content. And the data is, I think, reconfirming my assessment that the planet went past the tipping point, the major tipping point back in the mid-90s. We're seeing it not only with the ocean heat content, but we're seeing it reflected in the salinity contrast data, the temperature data, the stratification data as well. So it's going to be very interesting as more and more of that heat diffuses back to the atmosphere or through other processes is put back into the atmosphere. So I hope you found this video informative. And thank you for your time. And we'll talk soon. If you stuck around to the end of the video, thank you for watching. Be sure to give this a thumbs up, as it really helps the channel. And if you can, please support me either on Patreon and or buy me a coffee. Details in the description box below. Thank you.